Howdy, this video is on bond enthalpies. Bond enthalpies can be used to calculate the change enthalpy for a reaction. Using bond enthalpies to calculate change enthalpy for a reaction illustrates what happens during the reaction, so it can be very helpful. After watching this video, you should be able to describe how bond enthalpies are related to the electrostatic interaction. You should be able to put a series of bonds in order of increasing bond enthalpies. You should be able to describe how to calculate the change enthalpy for a reaction, and you should be able to calculate change enthalpy reaction using bond enthalpies. And so there's many different types of enthalpies, and they differ based on the subscript, and they all correspond to a specific type of reaction. If you have the R, that corresponds to enthalpy reaction. That's pretty generic, and it can be positive or negative. The subscript F corresponds to enthalpy of formation. You're going from elements to their steady state to one mole of the product. That can also be positive or negative. VAP means enthalpy of vaporization, going from a liquid to a gas, and that's always positive. FUS corresponds to enthalpy of fusion, going from one mole of a solid to one mole of the liquid. That's also always positive because you always have to add heat to the solid to make the liquid. The C corresponds to enthalpy of combustion because you're producing heat. That means the enthalpy is always going to be negative. L corresponds to lattice enthalpy, going from ionic solid to gaseous ions. You always have to add heat, and so lattice enthalpies are always positive. Remember, the ionic solid is much more stable than the gaseous ions because of the ion-ion interaction. HYD is the enthalpy of hydration, going from the gaseous ions to the aqueous ions. And so the aqueous ions, you have the ion dipole interaction with water, and so that's more stable. And so you're always going to have to, so heat will be released, and your enthalpy of hydration is always negative. Enthalpy of solution, solvent plus solute goes to solution. That can be positive or negative. And if you add that B, that corresponds to bond enthalpy. And so you're going from a molecule to fragments. And bond enthalpies are always positive because it always takes heat to break a bond. And so bond enthalpies is the change enthalpy when a chemical bond is broken in the gas phase. And so it's very important that you remember in the gas phase. So you can imagine that you're going from molecule to fragments. And so here we have butane. If we break a carbon-hydrogen bond, then we get that plus the hydrogen atom. And so the change enthalpy for this reaction is a bond enthalpy. Now, bond enthalpies are important because, again, we can calculate change in enthalpy for a reaction by using bond enthalpies. The sum of the bonds broken minus the sum of the bonds formed. And again, by calculating change enthalpy for a reaction using bond enthalpies, we can actually see what happens during a reaction, what bonds are broken and what bonds are formed. Now, the other two ways of calculating change enthalpy for a reaction, we can use enthalpies of formation, doing products minus reactants, or we can use Hess's law because they change enthalpy about one path is change enthalpy about another path. And so if we know a series of reactions that equals the reaction we're looking at, we just have to add up those delta H's. And so as two atoms get closer together, the electrostatic attraction between electrons and nucleus increases. So you can imagine that the electrons in this atom start being attracted to a nucleus in the other atom. Stronger electrostatic attraction, lower the energy, the more stable. Now, if the two atoms get too close, then you have nuclear repulsion, and the stronger repulsion, the less stable, the higher the energy. And so the bond energy is the amount of energy needed to break the bond. And so imagine we can set 0 as when the atoms are infinitely far apart. And so the bond energy, same as dissociation energy, is the distance between this minimum up to 0. Bond enthalpy is a little bit different. Bond enthalpy is the change enthalpy of the fragments minus the molecule. Remember, we're looking at a molecule going into fragments, and so that would be products, the fragments, minus the enthalpy of formation of the molecule. And so if we're thinking about breaking the hydrogen bond between two hydrogen atoms, our products are going to be the two hydrogen atoms, so 2 times the enthalpy of formation of hydrogen atoms minus enthalpy of formation of H2, and so that would give us a bond enthalpy of 436. And again, bond energy and bond enthalpy a little bit different. Now, most bond enthalpies are actually an average. And so if you think about the carbon-hydrogen bond, there's many, many molecules with carbon-hydrogen bonds. And so if we want the bond enthalpy for the carbon-hydrogen bond, we actually have to take an average. And so you can imagine that we have methane ripping off a hydrogen atom, so we can do the bond enthalpy here. Here we have ethane removing a hydrogen atom, and so it's going to be the carbon-hydrogen bond enthalpy. Again, breaking the carbon-hydrogen bond, breaking carbon-hydrogen bond. And so we take all these instances and we take the average, and that will give us the average carbon-hydrogen bond enthalpy. And so one reason that calculating delta H using bond enthalpies may not be as accurate as we'd like is because a lot of the bond enthalpies correspond to averages. Now, some of the bond enthalpies are exact. There's only one hydrogen-hydrogen bond. There's only one nitrogen-nitrogen triple bond. There's only one oxygen-oxygen double bond. And so all these are exact, therefore specific bond breaking. But if you have like a carbon-hydrogen bond, there's many examples of that. And so the carbon-hydrogen bond enthalpy is an average. Now, there's two main considerations determining the relative strength of the bond, and hence the bond enthalpy and the bond energy. And so the most important consideration is the number of electrons being shared. The more electrons being shared, the stronger the bond and the shorter the bond, and hence the higher the bond enthalpy and the higher the bond energy. And so nitrogen has a triple bond, O2 has a double bond, and F2 has a single bond. And so the N2 is going to be the stronger bond. So N2, you have a triple bond. Remember, the bond order is the number of pairs of electrons being shared. And so each line corresponds to a pair of electrons. And so we're sharing 3 pairs of electrons. That corresponds to 6 electrons. That gives you a bond order of 3. Remember, the more electrons being shared, the shorter the bond, because the nuclei can get closer, and the stronger the bond. And so the triple bond is the strongest and the shortest. The double bond, here we got sharing 2 pairs, and this corresponds to 4 electrons. It's a little bit longer than the triple bond and a little bit weaker than the triple bond. And then the fluorine-fluorine single bond, we're sharing 1 pair of electrons. So that gives you a bond order of 1. 2 electrons have been shared. It's a little bit longer than a double bond, and it's a little bit weaker than the double bond. And so the most important consideration in bond energy is number of electrons shared. We can look at another example. So here we have a carbon-oxygen single bond. So 1 pair of electrons being shared. Double bond, 2 pairs being shared, so that's a bond order 2. Triple bond, so 3 pairs of electrons being shared, and so that's a bond order 3. Again, the triple bond is the shortest and strongest bond. Now, the secondary consideration is the size of the atoms. The smaller the atoms, the closer the atoms, the stronger the bond. And so here we have HF, HCl, HBr, HI. And so fluorine is smaller than chlorine, smaller than bromine, smaller than iodine. And so that HF bond is the strongest of these 4 because the fluorine is the smallest, and so the HF will be closest. If we look at another example, here we have H2, Cl2, Br2, I2. And so again, in general, the smaller the atoms, the closer the atoms, the stronger the bond. And so in terms of bond strength, more electrons being shared means larger bond order. Remember, bond order is just the number of pairs of electrons being shared. More electrons being shared, the closer the atoms, the stronger electrostatic attraction between electrons and nucleus. The smaller the atoms, the closer the atoms, the stronger electrostatic attraction. The stronger the attraction, the larger the bond enthalpy, larger the bond energy, the lower the potential energy, the more stable. And again, the most important consideration is the number of electrons being shared. And so I mentioned that we can calculate the change enthalpy for a reaction using bond enthalpies. And so we take the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. Now, the change enthalpy of a reaction can be positive or negative. So what you calculate can be positive or negative, but bond enthalpies are always positive. And so this is often a confusing part. Again, bond enthalpies are always positive, but when we calculate change enthalpy for a reaction, that can be positive or negative. Another confusing part is when we're doing enthalpies of formation, we always do products minus reactants. When using bond enthalpies, it's broken minus formed. Now, the bonds of the reactants is broken. The bonds of the products are being formed. And so it looks like we're doing reactants minus products, but we're not. The way of thinking about this is that to break a bond, you're going to have to add heat. And so that will be a positive number, a positive change in enthalpy. When you form a bond, heat will be released, and that corresponds to negative change in enthalpy. And so again, please don't get confused. If using enthalpies of formation, it's products minus reactants. If using bond enthalpies, it's bond enthalpies of the bonds broken minus formed. And again, if you're breaking a bond, you're adding heat, so that's increasing the delta H. If bonds are being formed, that means heat's being released, and so that would be a negative contribution to your delta H. And so if we look at an example, here we have N2 plus 3H2 going to 2 ammonia. Now, if we want to figure out what bonds are broken and formed, we should draw the Lewis diagram. And now we just do bonds broken minus bonds formed. And so for the reactants, we're breaking a nitrogen-nitrogen triple bond, and we're breaking 3 hydrogen-hydrogen single bonds. And so here's our bonds broken, the 944 for the triple bond, and 3 times the 436 for the single bonds. And then we're forming 1, 2, 3, 4, 5, 6 nitrogen-hydrogen bonds, and each nitrogen-hydrogen bond has a bond enthalpy of 388. And so that gives us a delta H of minus 76. And so that's a negative delta H. So heat's leaving the system, and so that would correspond to an exothermic process. We can look at another example. So here we have methane plus oxygen goes to CO2 plus water vapor. And again, here's our bond enthalpies, the table of bond enthalpies. And again, so for the OH bond, that's in many different molecules, so this is going to be an average. The HH is for a specific molecule, so that's not really an average. That's not an average. The carbon-hydrogen bond enthalpy is from an average, carbon-carbon from a bond average. You notice that you have to make sure if you have a single bond, double bond, or triple bond, etc. And so again, to do the bond enthalpies, we figure out, okay, what's broken and formed, so we draw the Lewis diagrams. And then, so we're breaking 1, 2, 3, 4 carbon-hydrogen bonds, and we're breaking 2 oxygen-oxygen double bonds. And so 4 times 4, 12, plus 2 times 2, 496. And then we're forming 1, 2 carbon-oxygen double bonds, and we're forming 1, 2, 3, 4 oxygen-hydrogen bonds. And so that gives us minus 698. And so negative delta H corresponds to an exothermic process. If we look at one more example, here we have carbon gas going to plus water vapor going to CO2 gas plus 2H2 gas. Remember, you can only use bond enthalpies if all the products reactants are in the gas phase. Now we can actually calculate the delta H here using enthalpies of formation, bond enthalpies, and Hess's law, just to compare the different values. And so if we want to do enthalpies of formation, we do products minus reactants. Remember that elements in a standard state have 0 enthalpy of formation. And so we got products, CO2, 2 times H2, minus reactants, carbon gas, plus 2 times H2O gas. And remember, elements in a standard state are 0, so the enthalpy of formation for H2 gas is 0. Remember, you also have to bring those 2's down, and that 2 down. And so we do the calculation, and we get minus 627 kilojoules. And so that's going to be exothermic. And so that's what we get for enthalpies of formation. Now, if we want to do bond enthalpies, again, we draw Lewis diagrams to see which bonds are broken, which ones are formed. And so we're breaking 1, 2, 3, 4 oxygen and hydrogen bonds. And we're forming 1,2 carbon-oxygen double bonds, and we're forming 1,2 hydrogen-hydrogen single bonds. And so broken minus form, and we get minus 506. And so we've calculated the change enthalpy for the reaction using enthalpies of formation and bond enthalpies. Now, a final way of doing it, we can use Hess's law. And so we need to come up with a series of reactions, when added up, come to the reaction that we're looking for. And so we can imagine carbon gas going to carbon solid. And so the enthalpy of formation here, the change enthalpy for this reaction would be negative enthalpy of formation of carbon gas, because enthalpy of formation carbon gas would correspond to carbon solid going to carbon gas. We flip that, and so that's why it's a negative one. The enthalpy of formation for CO2 gas is going from carbon solid plus O2 gas to CO2 gas. So that's just enthalpy of formation. And then we have the enthalpy of formation of H2O gas, but we're flipping it and multiplying by 2. So minus 2 times the delta HF of H2O gas. Now if we add these three reactions, notice that carbon solid cancels, O2 cancels, O2 cancels. We get the reaction that we're looking for. We add the corresponding delta H's, and we get minus 627. And so, using enthalpies of formation, we get minus 6.7. Using Hess's law, we get minus 6.7. Those are the most accurate ways. Calculating using bond enthalpies, typically we consider it as an estimate. But again, it's helpful using bond enthalpies because it shows us actually what's happening during the reaction, which bonds are being broken, which bonds are being formed. And so using bond enthalpies is the least accurate method, but it is helpful. So hopefully you can describe how bond enthalpies are related to electrostatic interaction. Again, it's the interaction between the electrons and the nuclei. You should put a series of bonds in order of increasing bond enthalpies. Hopefully you can now describe how to calculate change enthalpy of reaction using bond enthalpies, and hopefully you can calculate the change enthalpy of reaction using bond enthalpies. I hope that helped.